for the kind invitation and giving me the opportunity to tell something that we have recently done. What we have done is basically we try to find out from this DESI, BAO and DES supernova data that if there any special redshift in the universe, means especially in the low redshift region, and if you can find out those special redshift, and if we can measure the Hubble parameter at those special redshift in a kind of a model independent way, and if you can do that, comparing with the Planck, if they are consistent with the Planck or not. The idea is basically, Frank, that already in the from the DESI results, people have shown with some particular parameterization that there is a sort of evidence from dynamical dark energy or deviation from the lambda CDM. So we try to find out if there is any special redshift in the low redshift regime which actually is driving this deviation from this lambda CDM. And in doing so, we also use the same technique for the growth data that I will describe, and it allows us also to measure the growth factor directly from the background quantity. Usually, it's difficult to measure the growth factor because it comes with the bias. So instead, we usually measure the redshift space distortion parameter, F sigmoid, and this also needs the information from the sigmoid. So here we will show that it may be possible at some very special redshift that one can measure the F or the growth factor directly, and it may help later on if you can measure the 21 centimeter power spectrum or others in that specific redshift. One can get the information for the bias also. Okay. So it's very quickly that after Planck 2018, we know that the lambda CDM model is one of the best model. It actually fits very well the Planck data. Not only Planck data, the data at that time available, the BAO and the supernova data, and it's mostly driven by these three parameters, at least at the linear level of fluctuation. But recently, not recently, I think another last 4 or 5 years, there are two problems with this lambda CDM. Everybody knows, I will not go very detail, that there is the Hubble tension. The one Hubble parameter is measured through the history of the physics of the early universe, which needs a cosmology, and Planck assumed this lambda CDM cosmology. And the other is basically measured from the astrophysics of the stars by this Schu's measurement, and they are roughly deviating by 10%, around 5 sigma, fine. Still we don't know whether this tension will actually the tension or there is some systematics involved, but in time maybe we'll know it better. Also now we have these results from the DESI DR2, assuming a sort of a deviation from the lambda CDM, parameterizing it through this kind of parameterization. And it actually gives the region, allowed region in the parameter space, which is very, very far away from the lambda CDM. I mean, it's more specifically around 4.2 sigma or 4.3 sigma. And taking different combination itself is actually this results is quite robust. Note that deriving this result, there is no assumption of this Schu's prior. So these results is not driven by the Schu's prior. This is there in the DESI data and all other data. But the question is that is it really a new physics beyond the lambda CDM, or this is just sort of a artifact of the CPL parameterization? People are doing this thing. There are a lot of papers just to try to see that with different parameterization or different dark energy model, whether these deviation from the lambda CDM is still existing or not, fine. So we'll try to do it, but in a sort of a different way. So this is just the basic equation that we know for the background cosmology. Let's say for the timing we are concentrating on the background cosmology. And they are, mostly we have these two observable. One is the angular diameter distance. We measure it through the BAO or the CMB acoustic scale. And then there is the luminosity distance that we measure through the supernova flux, fine. And the idea is that what we do, we just assume a equation of state for the dark energy like CPL parameterization. We go through all those things, calculate the H, then calculate dA, dL, and with the data we just constant the parameters of this equation of state, fine. Our idea is to go backward, that from the data directly, because the data are available in DL and DA, so we really try to reconstruct this DL and DA independently, and then go back. As you can see that here, in this equation, if I go back, I can reconstruct the H. And from this equation, this is the pressure of the dark energy. If the pressure of the dark energy is not constant, then gives you a very strong hint of that whether the dark energy is a lambda CDM length cosmological constant or not. It cannot give you directly the what kind of dark energy, but it can at least gives you the information that whether the dark energy is a cosmological constant or not. And for that, you don't need any information from the matter, because most of the time doing this way you need the information from the matter, but going this way just from here we don't need any information from the matter. Fine. So what we do, let's say angular diameter distance. So the Hubble parameter is related by the angular diameter distance with this angular diameter distance and its derivative. But can we do better? Is it possible to get the information of the Hubble parameter just from the distance itself without taking into account the derivative of the distance? Fine. So let's plot this angular diameter distance. So this is the angular diameter distance, and always this angular diameter distance peaks at a point at some redshift. Fine. And if you plot the derivative of the angular diameter distance, remember that they are plotted in the defined scales. So this is a redshift where these two values are actually equal. Okay. So there are two redshifts, special redshift, where the angular diameter distance maximizes, and a redshift where the angular diameter distance is equal to its derivative. Okay. So if you take this thing, so at where the angular diameter distance maximizes, so then at that point dA prime is 0, so H is directly equal to the angular diameter distance. And when it is crossover, means the distance and its derivative crossover, then the Hubble parameter also related directly to the angular diameter distance, because I can replace dA prime by dA. Fine. So there is at least two redshift where I can get the Hubble parameter directly from the angular diameter distance. Fine. But I can do more. Fine. I can use now all other distances like the dl or dm, their derivatives, and I can actually have 7 redshifts where these derivatives are equal to the distances. So actually we can get 7 redshifts. The redshift 3, Z3 and Z7 is basically the angular diameter distance derivative, and it's equal to the derivative. And the others are actually coming from the distances of the luminosity distance or other. So there are 7 redshifts where I can actually get Hz directly from this dA parameter. Fine. So this is for the background. Fine. Now let's see what happens to the part of the universe. Fine. In the part of the universe, I have this matter density contrast. This is the growth factor. As I said, that we cannot directly measure the growth factor. What we measure is the F sigmoid, the redshift space distortion. This is driven by this equation. But now if you plot the F sigmoid, the F sigmoid also maximizes at some point. This we have plotted with the Planck lambda CDM base fit, but it also has a maximum value. Fine. Now we constructed a diagnostics like this. So as you can see, this quantity Ez is H by H naught, W is the dark energy equation of state. These are background quantity, but the F is sitting over here, the growth factor. Now the interesting fact is this Sz, that where it maximizes, this Sz is actually identically 0. So Sz is identically 0, I can actually get at least this redshift, the value of F just from the background quantity. So I can constant the background quantity very, very accurately from defined data, and at least at this redshift I can get the growth just from the background quantity. Okay. So this growth factor can also be determined just from the background quantity at this Z equal to Z max. Okay. So these are the idea. So now let's use this defined data and just to see that what is happening. Okay. So this is the work that I work with Purva sitting over there. So we take defined data, the DESI data supernova, the DESI data, and also we fix these are pair that we fix the acoustic scale or the distance to the last scattering surface as given by the Planck value. Fine. So we are not assuming any early dark energy or any modification of the early physics. So we are fixing that this acoustic scale is fixed as given by the Planck. So that is our sort of you can say an anchor. Fine. So these are the data, and what we did that we basically reconstruct the moving distance and its derivative, and from that I can reconstruct the dA, dl and their derivatives. Actually we reconstructed the dimensionless distance, which is this, for all these distances, and then we can reconstruct the E, which is the H by H naught. Okay. So that is the program. Now there is two reconstruction program that we use. First we use this multitask Gaussian process. We use defined kernels and reconstructed this value and get this 7 redshift point. Once we get this 7 redshift point, what we did a knot-based spline method. So we take the knots at this 7 redshift point and do a spline for the 3rd order or 4th order or 5th order, and again reconstruct this thing and see that whether they are actually consistent or not. Fine. So that is the program, the data, and this is the reconstruction program. Fine. So these are the reconstruction. I am showing it for just one kernel, but all the kernel that I have used here, that I mentioned, there are 4 or 5 kernels, the results are completely robust and they are absolutely similar results. Okay. So these are one reconstruction of the DM, DM prime and DM double prime. This blue is our reconstruction, is red is basically the Planck. So as you can see that they are already showing some sort of difference from the Planck. And these are all these distance and their derivative and all these 7 redshift points that we have can get from here. And then once we have the 7 redshift point, we get the DA, those redshifts that I showed earlier, and also the H or E by, H by H naught at the 7 redshift points. So what is the result? So this is the results, fine. So these are the 7 redshifts that we have. These are basically that I mentioned. This is basically where DA prime equal to 0, and this is where DA equal to DA prime. And these are other redshifts, means like where the DA is equal to DL prime, DM equal to DM prime, and so on and so forth, fine. So these are the 7 redshifts, these are the values of DA from that 7 redshift that we have. These are the Planck values that we can get from the Planck chain. So these at these redshifts for this DA. At the DA, the tension level is basically this, fine. And then we get this reconstruction E that I showed over there, that how you can get H, and then H, H by H naught you can get E. And these are the value in E and E Planck. And as you can see, the tensions are quite high, fine, around 5 sigma kind of tension at these 3 redshifts. And if you go to higher redshifts, these results going exactly to the Plancks, fine. So at redshift like more than 1, practically there is no tension. So it actually shows that these are the kind of a redshift regime where there is a tension, there is some sort of a strong deviation from the lambda CDN. But as you go beyond that redshift, more higher redshift, the things go smoothly to the Planck value, fine. This is for this multitask Gaussian with that one kernel, and as I said, all the results are similar to different kernels. And this is when you do this knot-based thing, that you take these 7 redshift, take them as knots, and then you spline kind of thing. So here we did the 3rd order, means cubic spline, 4th order spline or 5th order spline. The results I am showing is for the 5th or 4th order spline, but the 3rd order spline or 5th order spline, they are also the similar results. And as you can see, the behavior of this thing is basically same like as I showed for the Gaussian process. And again, the tensions are little bit less because the error bars here are a little bit higher, but the pattern continues. That at the at the low redshift, around redshift 1.3 to 0.5 or something, there is a strong tension with the Planck thing. But as you go to the higher redshifts, these things actually goes to the Planck results, fine. So these actually encourages us that, and as I said, that here we have not used anything like shoes measurement. So everything is Planck prior. So within the Planck prior itself, at this redshift, as you can see, there is a strong anomaly with the tension with the Planck values. Fine, that is there in the data, and the results are quite robust. Whatever way the reconstruction you use, at least here, the different Gaussian in the Gaussian process with different kernels, or the knot-based process with different orders, all of them give you the same kind of results. Fine. Now these are the reconstruction that define the rho dark energy, the pressure of the dark energy, and the null energy condition. Okay, this is the null energy condition. And as I said, that from here the pressure constant is not consistent with our reconstruction. There is a 2 redshift regime around here that I already showed, and here that there is a strong deviation from the constant pressure. For the null energy condition, there is an indication that there is a violation of the null energy condition, so it just goes to the phantom. But okay, the error bars here are very big because we don't have many data beyond redshift 1, so we cannot constant that much. But at least for the low redshift, things are consistent. I mean, it is not cosmological constant, fine, but it is consistent with the null energy condition. So the results are more or less consistent what people get with the CPL parameterization. So now let's see that how it. What happens with the CPL parameterization? Let's say you have the CPL results with the CMB, all these chains, you do the same thing for the CPL and compare with us, fine. So this is the results, fine. So this is the Planck numbers, the red points are basically the Planck numbers at this 7 redshift, fine. And the blue points are our knot-based reconstruction, and the green points are basically the CPL chains that we use with the Planck DESI DR2, Planck DESI DR2 and the DESI DES5. And as you can see, these three redshift points that we have, that I shared, that there is a strong constraint or strong tension from the CPL thing, the exactly same thing happens. So our results is completely inconsistent with the CPL, and in a sense that it actually also says that whatever you are getting from the CPL things are more or less the same, is robust, because we are completely model independent reconstruction. And most probably the tension or the deviation from the lambda CDM which is there in the CPL, they are actually driven by these three redshifts, or the HZ at these three redshifts. Fine. So, and now as you can see that the EZ, so this is our reconstruction for the EZ, and this is the CPL. This is the reconstruction for the DM, and this is for the CPL, fine. Deviation from the lambda CDM, and our results and CPLs are actually quite consistent, fine. There is an interesting thing, as you can see over here, this E has a sort of, or the H has an increased value from the lambda CDM around this redshift point where I was showing, and the DM is basically has a minimum and again going that. So it actually showing that if you look at the supernova, or let's say you have a lot of supernova here, what it actually predicts is that around this redshift, the DM is actually going down, so you start getting this supernova looks brighter than what the Planck actually predicts, but this brightener, in the brightness of the supernova that is brighter, it actually attains at some redshift maximum brightness or maximum brighter, and then again it reduces. So there is a non-trivial jet dependence of this deviation from the thing. Fine, it most probably may not be sort of addressed to some systematics in the supernova. So there is a non-trivial jet dependency here. Okay. So this we find is quite interesting. I have 1 minute, fine, maybe. Okay. So and these are basically our forecast for the AP test. These are our numbers, and these are basically what we can get from Euclid. And as you can see, these 7 redshifts, the Euclid numbers are quite suppressed. So maybe if you do this thing afterwards with the Euclid number, so things will be more tighter actually. Okay. Just go to the now this F sigma that I showed over here. So we did this thing. This is a paper with Topomoy, Guhasarkar at BITS Pilani and his student. So we did the same with the F sigma data. So there is 2 things we have done. We did only the SDSS data where we have around 5-7 data that we did, and also all the F sigma data that is currently available. Fine. Interesting fact is that if you take the only SDSS data, nothing else, no supernova, nothing, you do the same DA and DA prime, that reconstruction, that DA prime is 0 and DA equal to DA prime, you get the same, exactly same redshift. Okay, that's the thing. And at the 2 redshift, your EZ only in the SDSS has a 2 sigma deviation from the lambda CDM, and here there is no deviation, which is consistent with our result. But in the SDSS itself, at this redshift where DA equal to DA prime, you get a 2 sigma deviation without any supernova or anything, fine. We also, as I said, from this F sigma, the highest, I mean, where it maximizes, we get the redshift, which is basically this for this SDSS data point, or all the full supernova data, we get this kind of value. Okay, and then we can get the F value over here. As you can see, the central values are quite different, and the central value is smaller than the Planck value, which is also consistent because we get this value around this region. H is higher. If the H is higher, there is a more Hubble friction and the growth will be smaller, fine. So that actually also showing over there that we get around this redshift 0.4, which is around exactly where we get the higher values, that the growth is actually smaller. For SDSS, obviously the error bar is big, so we don't get any any tension with the Planck. But if this value remains same with the DESI data, we can do it. Still now this whole DESI full shape likelihood is not released, but one can do it there. And if this value remains same, but this value get reduced quite a lot, then maybe some tension will also come over here. And once you get the F, I mean, you can use the 21 centimeter line power spectrum, you can actually get the beta parameter from the RSD, and then using this F, you can actually get the information of the bias at this redshift. Okay, so we cannot do that at this moment, but that can be possible because we can now get F measured at some particular redshift, low redshift, very accurately from the background measurement. Okay, so this is all that I want to share with you. So these are the conclusions. So I stop here and I can take questions.
What stops you from playing the game again and again? Like you said, at some point DA is DA prime. I can have a point that DA prime is half of DA.
No.
Or some numerical factor times DA.
You can do.
You just get an extra pre.
No, you can do, but if you do it, if you can do it, okay, where I go? You can take any value over there, but then where you go? Okay, let's see here. Yeah, so you say that, okay, I get dA prime some 1/3 of dA, fine, and then some points over here, fine. But we tried that, I mean, it's like we are doing that, not only that, we can actually do the dA double prime also, okay. At this moment, the redshift that you get there, maybe the data are not that thing that you don't get meaningful constant from there at those points, right? So, but that can be done. I mean, if we get those things.
Yeah, one very brief question. Where you see that, maximum deviation from Planck, does that depend on which supernova sample you
Okay,
use?
so we have currently used the DESI data, but we are now doing just check these results with Pantheon Plus and Union, but maybe we'll get the results very soon. But yeah.
Hi, thanks for a nice talk. So one comment at first is about the shoes calibration. So even all the high-resolution DES Pantheon Union data sets are calibrated with shoes as from low redshift. So the mu distance modulus minus distance modulus fiducial is calibrated to a zero line, assuming shoes prior for redshift below 0.01.
0.1 or 0.2?
0.01.
Okay.
So the low redshift calibration is already done. So all these statements are assuming shoes calibration of supernovae for DES, Union, and Pantheon. So that's the only thing that they do, and then they extend it to high redshift. And
actually, I mean, this is the thing that also means this FSU also mentioned that there is a problem of calibration at the very low redshift, fine. And we did that, so we take this defined of calibration, fine. And we actually get that these results are not much dependent upon this calibration. So let me, if I have the slide. Yeah, so what we did, like from the DES results, so we get a shift at the very low redshift, this kind of shift that the FSU has mentioned, and we did the redone the calculation, and we are getting around more than 3 sigma.
So DES samples have photo-z redshifts errors. If you consider the Pantheon, which is 1701 number of supernovas, you will see that the amount of departure you see from the results in comparison to DES Y5 is more.
Okay.
So Pantheon is more substantially contributing to the signal.
Okay.
You can calibrate it at a low redshift, but the in between redshift 0.5 to 0.7, there's a significant departure, which happens.
Okay.
This is a comment on the calibration. You can see one of the DESI plots, which shows that there's an overall calibration error, which is they just subtract a number so that it looks like around zero. They said it's in the paper.
Okay.
Another point is about the omega matter. Omega matter is inconsistent between Planck 2018 Act later and
Assuming a lambda CDM model. Assuming a lambda CDM.
Yes. So how do you include that?
No, but we don't need omega matter here at all.
No, but when you are fitting it, you will need at the anchor redshift values, the amount of omega matter density, whether it is going to lambda or not.
No. So see that what we are doing, we are having the DA or DL values, fine. So you are directly reconstructing DL and DA, fine. And from there, that the method that I mentioned, I can directly get the H. So I don't need omega matter here at all.
No, what I'm trying to say is when you equate the two derivative with the DA, there omega matter enters in that particular Z choice, right?
No. See again, I have this DA.
You are just reconstructing at that.
DA, fine, and then I can also get the DA prime from their reconstruction, fine, and then I just calculate H from there, fine.
So do not assume any value.
No, this whole exercise is absolutely independent of any cosmological parameters.
So then maybe it is going to a lambda because of the similar value of omega m, which
maybe, but in this exercise there is no omega matter dependence actually.